Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on modeling heteroscedasticity, and in this lesson I'll introduce one of the simplest time series model to model the condition of variance, so-called the arch model. Let's assume we begin with fitting an ARMA model to a time series YT as provided on a slide, where the residual process is ZT assumed to be white noise with constant variance given by sigma squared. However, in many applications, the time series data often exhibit volatility clustering, where time series show periods of high volatility and periods of low volatility, indicating non-constant variance. If such, we can rewrite the error term ZT as the product between a deterministic but time-varying component, sigma t, and a random process RT with mean 0 and variance 1. In this lecture, we'll focus on modeling the volatility sigma t. We'll begin with one of the simplest time series models introduced by Robert Engel in 1982, the autoregressive conditional heteroscedasticity, or in short, ARCH model, used to model the time-varying volatility often observed in economical time series data. For this contribution, he won the 2003 Nobel Prize in Economics. Arch models assume the variance of the current error term or innovation to be a function of the actual sizes of the previous time period's error terms. Often the variance is related to the square root of the previous innovations or error terms. The Arch family of models assume that the volatility, or sigma t squared, is a linear function with lagged values of the mean equation errors zt. Thus, the time series dynamic of volatility is like an AR process. Specifically, the squared errors zt are modeled using an AR process where gamma 0, gamma 1, and so on are the error coefficients at omega t, and omega t is the error assumed to be uncorrelated with mean 0 and variance lambda squared. The expectation of zt squared given past history of the error process is equal to the error polynomial for zt squared. But the expectation of zt squared is also equal to sigma t squared. Hence, we model the condition of variance as a linear combination of past squared error terms, gamma 0 plus gamma 1 times zt minus 1 squared plus gamma 2 times zt minus 2 squared, and so on. In the introductory statistics courses, it is often mentioned that independence implies zero correlation, but not vice versa. A process, such as the arch process, where the conditional mean is constant but the conditional variance is non-constant, is an example of uncorrelated but dependent process. The dependence of the conditional variance on the past causes a process to be dependent. Thus, in arch models, the conditional variance has a structure very similar to the structure of the conditional expectation in an error model. I explained this concept with the simplest arch model, arch of order 1. We'll consider here yt to be the mean, which does not vary in time, to be a process with a mean which does not vary in time, plus the zt process, which is modeled using an arch 1 model. That is, the conditional variance is equal to gamma 0 plus gamma 1 zt minus 1 squared. Note that sigma t is assumed deterministic. The best ct are assumed given and hence realized at time t. However, we do not observe volatility with certainty. The true volatility of zt is sigma t squared, which is deterministic, plus omega t, which is random, where omega t has mean 0 and variance 1. Those two processes are also assumed uncorrelated. Together, this leads to the AR1 equation for zt squared as provided on the slide. This equation is crucial in understanding how arch processes work. If zt minus 1 has an unusually large absolute value, then sigma t is larger than usual, and so zt is also expected to have an unusually large magnitude. This volatility propagates since when zt has a large deviation that makes sigma t plus 1 squared large, so that zt plus 1 tends to be large, and so on. Similarly, if zt minus 1 squared is unusually small, then sigma t squared is small, and zt squared is also expected to be small, and so forth. Because of this behavior, unusual volatility in zt tends to persist throughout, but not forever. Because of the characterization of zt squared as an AR process, we can further obtain the conditions of stationarity of the arch model for a time series yt. The conditions are as follows. The unconditional expectation of the time series is mu. The unconditional variance of yt is the variance of zt squared, which can be shown to be equal to gamma 0 divided by 1 minus gamma 1, where gamma 0 and gamma 1 are the AR1 coefficients for zt squared. We also need to have that yt and hence zt are uncorrelated, because we assume that the variance is finite and positive under stationarity. Thus, gamma 1 needs to be smaller than 1. These are the conditions under the so-called weak stationarity. In order to ensure strong stationarity, we need to impose additional constraints on gamma 1 for ensuring that the fourth moment of zt is finite. The fourth moment, assuming normality, is provided on the slide. In order for this to be finite, we also need to impose the additional constraint that 3 times gamma 1 squared is smaller than 1. This is needed in the derivation of the quartuses, which is a measure of how fat the tails are. The quartuses of the arch-1 model under the assumption of stationarity is larger than 3, which means that an arch-1 model for zt has fat tails, and thus it is more likely to produce outliers than the simple normal white noise. This is a comparison of the distribution of distributions with different quartuses. For distribution with quartuses larger than 3, as the one in the middle, the curvature is high in the middle of the distribution and tails are fatter than those of a normal distribution provided on the right. A distribution of data with fat tails is frequently observed in financial markets. We can combine the arch model with an ARMA model as illustrated in the first slide of this lesson. Some specific examples are provided here. We can begin by assuming an AR1 process for modeling yt with mean mu and AR coefficient phi. Then the AR process zt can be assumed to be an arch-1 model. Hence, the conditional variance is gamma 0 plus gamma 1 times zt minus 1 squared. A second example provided in this slide is the ARMA 1-1 and arch-2 models, where yt is modeled by an ARMA 1-1 with zt, the error process, being modeled by an arch-2 model. Hence, the conditional variance is gamma 0 plus gamma 1 times zt minus 1 squared plus gamma 2 times zt minus 2 squared. It's important to note that when we have joint models, as provided here on this slide, we need to estimate them jointly. It's not good practice to first estimate the ARMA process for yt and then to apply an arch model to the residual process. We will discuss this aspect with a data example in a different lesson. How to estimate the arch coefficients or the arch model? The common approach is using the maximum likelihood estimation. Because the time series yt is not, the variables in the time series yt are not independent, then the likelihood function cannot be written as the product of the individual marginal distributions of yt. Instead, it needs to be decomposed as the product of conditional distributions. I'm introducing here the concept of conditional likelihood, as discussed in the first lecture on this course, reviewing essential concepts in statistics such as the decomposition of the joint distribution. We can decompose the joint distribution of the random variables yt minus 1 up to y1, modeled by an RP model using the unconditional likelihood as defined on the slide. The second term in the decomposition is a joint distribution of the first p random variables in the time series. Except for the small order arch models, this last term is difficult to express and therefore ignored if p is much smaller than t. Thus, in fitting an arch p model, we instead maximize the conditional likelihood defined on the slide. The maximization is with respect to the AR coefficients in the arch model. Since the estimation requires a numeric algorithm, it is only done using a statistical software such as R. In summary, in this lesson, I introduced one of the simplest models used to model the conditional variance or the heteroscedasticity in a time series, the so-called arch model. Thank you.